Good day, everybody. Today I want to look at trying to find if the gravitational pull at the top of a hill can be more than if there were no hill at all. Now, common experience tells us you definitely get lighter as you go up in elevation, air density decreases and so forth. But I'm going to analyze this and perhaps have a little surprising answer at the end. So first, here's a nice steep hill. This shape, by the way, would be from the shape of max gravity. If you put an object here and you could deform the mass into any shape, you want to maximize the pull, this would be that shape. Well, I took it to where it was at the widest. So if you just kind of took that shape, that would give me this hill. But it's a little complicated to do some of the triple integrals we're going to need. So the hills we end up looking at will be just simpler models. You know, the old joke for mathematicians or engineers, you know, assume a spherical cow. Well, here's our hill. Anyway, first some preliminaries. Obviously we'll use Newton's gravity, and we're going to kind of put the hill at the North Pole, so we don't have to worry about the z component of gravity. Here's the vector form. If I just look at the z component, it would be from this. We've got our point mass m at ABC. We've got some mass mu at xyz, and so this will be the pull. We're going to use units so that our planet has radius 1, mass 4/3 pi, so the density is 1, and units of time, so that gravitational constant g is 1. So that simplifies our force in the z component, force of gravity in the z component to be this. And we're going to sum up from everywhere in a solid, so we need a triple integral. And each mass mu will just be the density times the infinitesimal volume. So we end up with this triple integral that we have to do over the solid. So again, here will be our first hill. By the radius is 0.00002, and then the height is 0.000002. It's 1/10 the radius, but it's on top of the Earth. The North Pole being at the point x equals 0, y equals 0, z equals 1. So the z value everywhere at the top is 1 plus that height, or that value there where I put top. So that's the top there. Note, for if you rough estimate of the radius of the Earth as 4,000 miles, then the height ends up being about 42 feet, and the radius 420 feet. So that's kind of the shape of this hill I'm looking at. Now we can do this triple integral exactly, but I'll first ballpark it, and that'll be a good practice for what we have to do later when I can't get the integral exactly. Just to see what's going on, I'm going to magnify this. So here we are. I mean, this is actually the sphere right here, but it's such a small portion, you know, 420 feet for the Earth, that, you know, it looks flat. I'm going to graph a hill, the same scaling, but 10,000 times bigger. So here this hill has radius 0.2, and then the top's 1/10 that, for height 1.02. So this has the same scaling, but now we can see the curvature of the Earth. So for my approximations, the sphere has cylindrical equation r squared plus z squared equals 1. Or if you know r, then you can figure out z. It's just the square root of 1 minus the r squared. So we can get that z value there. So if it's 0.2 away, then square root of 1 minus 0.2 squared is that z value. So when I find the pull from this cylindrical hill, I'll first use an overestimate. I'll count everything from z at that value on up. Now that's going to count this part of the sphere a second time, because I'm going to do the sphere independently and then add those two pulls together. I'm going to find each force first of the hill and then of the earth or the solid sphere and add them together. But if I count z from this height on up, I'm counting that sphere part twice. So that'll be an overestimate of the pull from the disk. I'll also start at z equals 1, so that's where the North Pole is, and then I'll go from 1 on up, to 1.02 in this picture. And then that would be an underestimate of what the hill pulls. Right, so the true value is somewhere in between those two. And again, with our actual hill, it's not 0.2 and 1.02, but these are the r's, and then that's the top z. But then the bottom z is square root of 1 minus r squared still. All right, so let's look at those integrals. First, the pull downward, if we were just at the North Pole and there were no hill, would be 4/3 pi in the downward direction, so negative, because you can put all the mass for a sphere as if it were at the center, and that'll be at the origin. So that's the pull if there is no hill, if we're at the North Pole. But now with the hill, let's first find the disk first. This is the underestimate, so I only do z values from 1 to the top, 1.000002. So that's an underestimate of what the hill will pull. An overestimate, if I start from the z value of square root of 1 minus that radius squared, again, that counts part of the Earth twice when I include the Earth later. So this overestimates the pull downward. The actual pull downward is given by this. Right, so we want to go from the surface of the Earth up to this z value for those values of theta and r. For some reason, Maple wouldn't do this for me. I wasn't too worried because, I can do the theta integral or t integral first, and that'll give me 2 pi. And you can actually anti-differentiate this with respect to z. Got to work here if you want to see it, but I need this integral. If I do the z, you can rewrite it this way. You can do a u substitution is what's inside the parentheses there. Then du will be 2 times this dz, or du over 2 is that dz. So we're essentially integrating this du. Oops. Anyway, so that'll be that or this. And you could also just check derivative of this with respect to z. It'll give me that. If we want to plug in the limits that I had from the surface of the planet sphere up to here, then I just need to plug these into the antiderivative. Well, if I plug in this upper limit in for z, that's zeroed out, so I just get that, which will of course be -1. And now minus, so then if I plug in this in for z, I just get that, or subtracting the negative. You can write it this way. So there's the integrand, and here's the actual value then. Okay, so I did this theta integral first, got the 2 pi, and then the dz integral, and I got the -1 and this quantity. So now I just have to do that r integral, and you can do that numerically. And you can see it is in between these two values. So there's the overestimate. I counted the sphere part twice. If I do that, and here's the underestimate, and then here's the true value in between these two. So the force of gravity then is going to be this quantity plus the pull from the planet or the sphere, but we put all the mass 4/3 pi and then divided by r squared, but how far away are we? It's 1.000002. So that will be the z component of the force, which is the full component in the downward direction. Redoing it. Here we have it again. Same value, of course. But now I can compare it to if there was no hill, it's weaker. So I guess as expected, you have a stronger pull if there were no hill than if you're at the top of a hill. All right, so as expected. If you can increase the density of the hill, instead of having the same density, it would take about almost 1.5. So if I multiply by this density, now the pull downwards is actually more. So you just need something that's super dense. Now the average density of the Earth is 5.5 grams per cubic centimeter. And rocks on the surface are much less dense, around half. But if you had a hill made out of gold, that's really dense, or copper or lead, that would work too. But it would be hard to have a hill 420 feet in radius, 42 feet high. But if you did, you'd actually be heavier at the top of that hill than if there were no hill. So you might say that's the end of the story, but is it? Let's go back. If this is a person at the bottom of the hill, there's a pull downwards from the force of gravity, but there's also now a pull upwards, right? If the disk were the only thing, if there were no sphere, then, and you were right there, most of the pull would be in the radial direction towards this z-axis. But if you're at the bottom, is a pull upwards as well. So I'm going to compare being at the top of the hill to being at the adjacent to a hill at the bottom. So I'm going to put this, I'll put it at x equals 0, so it'll be above the y-axis. It's going to be at 0.00002 in radius away. For this picture, it's at 0.02 away. This is the 10,000 times bigger picture. Here's the actual hill again, but the Earth looks a lot flatter when you've only got 420 feet in radius. But so you've got a little pull upwards. So let's see. So there's also the radial pull, right? So there's the radial pull. That'll be just from the surface of or that'll be from the solid sphere. And then we have the pull from the hill. So here's a picture of the 10,000 times bigger hill. So you've got this point here. Radial would be 1, and the magnitude of the force in that direction is 4/3 pi. But the z component is the vertical, so that'd be like that. And then I have no x component, but there'll be a y component in this direction. Now, if this is 0.2 and that's 1, this will be the square root of 1 minus 0.2 squared, or square root of 0.96. So those are the sizes, and then these also give us the magnitude, right? So if I were to find the angle, see, cosine of that angle times this magnitude would give me the magnitude of the y component. But in the end, it would just be 0.2 over 1 times the magnitude of the force. So that'll be the y component. The z component, if I found that angle, would be cosine of that angle times this magnitude of the force, but that'll be the same as that length square root of 0.96 over 1. All right, so I mean, there's a force diagram, so we can get the y and z components of the force. Of course, the sum of the squares will work out. And again, we've already seen for a mass at ABC, the z component of the force is given by that. Well, now the y component is something similar. X, I'll ignore it by symmetry. If it's above the y-axis, if x is 0, it'll be 0. Just to see a lot of decimals here. With this radius, this will be the z value, roughly. And then the z component of the force of gravity. But 50 digits was too much. So let's look at it with 13 for the integrals. Of course, this matches, so 3949, 3949. All right, so that's the z component of the force of gravity when this is 0.00002. Now for the disk, again, there's a pull upwards. So we're going to do an upper and lower bound. The upper bound for the pull upwards is if you count from this z value all the way up to the top. But again, you're counting that sphere twice. The lower bound for the pull upwards is if you start at z equals 1. Right? So z equals 1 is right at the North Pole there. So if I start at 1 and then go up, that'll be a lower bound for what the disk pulls upwards. But if I start at this z value and go up, that's an overestimate of the pull upwards. So here is the underestimate of the pull upwards. That only goes from 1 on up. The overestimate of the pull upwards goes from that bottom z on up. So again, this value's bigger, but they're both upwards. So now if I add that to the force of gravity, which is downwards, the underestimate leaves me with the biggest magnitude. So that's this value right here. So that's the sphere z component plus the disk z component, the underestimate, that left me with the biggest magnitude in the downward direction, in the z direction. Here's a underestimate, at least in magnitude, of the pull downwards. Right, so these are very close, but this one has a little bit bigger magnitude. So that's the z component of the force. For the y component, it's just, here's the y component from the sphere. And now for the disk, now the sphere points it towards the origin, which will be in the negative direction. And to go in that same direction, an overestimate of the pull, I go from the bottom z on up. Again, so that counts part of the sphere twice. So this will be an overestimate of the pull towards the origin, the z-axis. An underestimate of the pull towards the origin is if I only count that part of the disk from 1 on up. So since they're both negative, the overestimate is given by the sphere and this value. And here's the underestimate in magnitude. So if I do the two overestimates in magnitude, that gives me the overestimate in magnitude that point mass feels from the disk and the sphere. Here's the underestimate. But if I compare to the magnitude, the absolute value of the Z component of the force on top of the hill, it's more than the overestimate, 785. That's 784. Of course, this is more than that. So this is the overestimate in both the Z and the Y put together. So this is the most magnitude of the force, and it's less than the force in magnitude of being at the top of the hill. So again, pictorially, you've got this force. It's not purely radial now because I'm counting the disk. It's mostly in the radial direction though. We found its magnitude. It got lessened because of the upwards pull of the disk, and it got lessened enough so that being at the top has a stronger pull downwards in magnitude than this does in magnitude in whichever direction it is. So in other words, if you had a scale at the top of this hill and a scale at the bottom adjacent to the hill, you're going to be heavier at the top than at the bottom. So a little surprising result. You won't see this on the Earth though, because of the density of the Earth is so high. 5.5 is one of the densest planets, and the rocks at the surface are roughly half the density of the Earth. So we would have a hard time even getting that 5.5 density for the hill. But if you could, keep it the same average, you had a uniform planet, you're actually heavier at the top of the hill than at the bottom. So there, it is possible, much to the surprise of our experience. All right, hope you enjoyed that as much as I did. Thank you, and have a good day.